The next topic, which is exciting topic that we will discuss today, is called the common mode response. And basically it says that how is the differential amplifier response or behave in terms of the common mode voltage. Remember, the common mode voltage doesn't have to be DC. It can be due to noise or electromagnetic interference. So it can be AC signal as well. It can be small AC signal, but it is common to both inputs of the amplifier. So the first condition we're going to study is what happened if we have a common mode input voltage but for perfectly matched differential amplifier. What happens to the common mode signal? How will the amplifier respond to that common mode signal? To show you how is the differential amplifier behaves, we're going to assume the following. We're going to say that here is the circuit. We have VDD, we have RD, then we have the Vout1 and Vout2, which are connected to the transistors M1 and M2, which are connected to the input voltages, and the sources are connected together, but they are connected to a resistor. We're going to call it RSS. That resistor is the equivalent resistor of the transistor, for example, or it can be just a bias-on resistor, and the V common mode voltage determines how much current will flow through this resistor. So over here we found the equivalent resistance of the transistor looking into the drain, or we have inserted a resistor at the source. By any means, there is an equivalent resistance at the source of M1 and M2. Then what we can do is we can find one equivalent half circuit for this amplifier. How are we going to get the equivalent half circuit? You have to keep in mind that this circuit is perfectly matched, which means that the voltage at the drains are the same, the voltages at the sources are the same, and the voltages at the gates are the same. Then we can combine these two transistors into one transistor, because it seems that every node in the two transistors have the same voltages. Then we will have a half circuit equivalent circuit for the common mode. Keep in mind that this half circuit is for the common mode circuit. The common mode half circuit says that we're going to have RD in parallel with RD, so from the top we will have 0.5 RD, because the two nodes of the resistors have the same voltages, so you can assume they are in parallel. And then this resistor is connected to a transistor, where the transistor is the two transistors in parallel. So basically this equivalent transistor will have twice the width but the same length channel. So this transistor will have twice the transconductance, 2 times GM, right? And then we will have the equivalent resistance at the bottom, which is RSS, and the gate is connected to the common mode voltage. So basically what we're saying is this differential amplifier, when it comes to the common mode voltage, we are stressing the common mode input voltage. This amplifier has one equivalent half circuit, and the two transistors will behave in parallel, and this will be the equivalent circuit. So this particular circuit is nothing but an amplifier. It's a common source amplifier with a degenerated resistance. Then the common mode voltage will be amplified at the output, and it will have the same voltage at both ends, right? Vout1 and Vout2 will have the same common mode voltage as the common mode voltage at the gates of M1 and M2. Vout1 and Vout2 voltages will also swing. Then we can say that the common mode voltage gain, we're going to call it AV common mode, will equal to Vx, which is the output voltage at the drain of this parallel transistor, over Vin common mode. And we know the gain for this amplifier is nothing but the top resistance over the bottom resistance. Then we can say that AV common mode, the gain for the common mode, will equal to minus the top resistance, which is RD over 2, over the bottom resistance, which is 1 over 2 times GM plus RSS. Keep in mind that the transconductance of this new transistor is twice the transconductance of M1 or M2. That's why you have 1 over 2 times Gm. It's twice the transconductance because the transistors are in parallel. So what we have said so far is that if we have a common mode input voltage and the circuit is exactly matched, then this common mode voltage, if it's AC, it will swing at the output. So we will see the same common mode voltage swings at the output. One will have it and Vout2 will have it, which is something that makes sense. Now we know how much the voltage will swing due to the common mode input voltage if the circuit is exactly matched. Now, another condition that we are interested in is what happens if the differential amplifier is not fully symmetric. For example, the first case, if RD1 doesn't equal RD2. When we fabricate these circuits, we will have deviations from the desired values. So it's not going to be, for example, 1 mega ohm resistance, it will deviate by percent, right? So that's something we have to live with. So now what happens if RD1 doesn't equal to RD2? That happens due to the tolerance of the fabrication process, for example. So what we're going to say is let the resistor of M1 to be RD and the resistor for M2 to be RD plus delta RD. So basically what we're saying is one resistor is perfectly matched while the other resistor is deviated by delta RD. It doesn't matter which one higher, which one lower, right? So you can always select the lowest value will be the actual value and the higher value deviated by delta RD. We can break this circuit into two half circuits very easily. If you will look into this resistor RSS, we know that this resistor RSS has a voltage across it called VB, and also the current through it is the current coming from both transistors, where each transistor has ISS over 2. So by breaking the circuit into two half circuits, we can see that the first half circuit will have a resistance equivalent of 2 times RSS, and the second circuit will also have an equivalent resistance of 2 times RSS. Note that the voltage at the source of each transistor will be Vp, then the current going through each half circuit through the bottom resistor is ISS over 2. So that's why when we break the circuit into two half circuits, we get the resistance to be twice as much because the current through each half circuit is half as much. So let's assume delta V common mode to be the change in the common mode input voltage. Then we know the M1 circuit behaves as common source amplifier with degenerated resistance. Then we can say that Vout1 will equal to minus delta V common mode times GMRD over 1 plus 2 GM times RSS. Also, the output voltage at V2 will equal to minus V common mode times GM times RD plus delta RD over 1 plus 2 times GM RSS. And the output differential voltage is given as the difference between Vout1 and Vout2. So we say that Vout1 minus Vout2 will equal to delta V common mode times GM times delta RD over 1 plus 2 GM times RSS. And basically the GMRD on the top cancels out for both terms. Now we can define the common mode differential gain due to the mismatch in RD to be A common mode to equal to Vout1 minus Vout2 over delta V common mode, and that will equal to GM times delta RD over 1 plus 2 times GM times RSS.